Assalamualaikum and hi everyone. So as I promised to you, we'll record about some guidelines to give you a brief idea how to do the tutorial 7. Okay, I'm not going to discuss very details. We're going to discuss this next week. Okay, and I really hope that everyone will try their best to answer. Okay, because this is a good exercise for the final assessment. Okay. Jangan tangguhkan kerja lah. It's better for you to do it now so that if you know something that you are not clear, you still can ask me during the class. Okay. Alright. So let me share the screen right now. Okay. Hopefully you can see clearly my screen. Okay, so question number 1. Okay, so actually the tutorial 7 I took the questions from the previous semester during the ODL punya semester. Okay, from the final assessment as well as from the assignment. Okay, so it is intended to produce propylene glycol, alright, by the hydrolysis of propylene oxide PO in a CSTR. Okay. So the type of reactor is in a CSTR. Okay, so this is the equation given. Okay, so the feed containing 3 mole per liter of propylene oxide and 30 mole of water. Okay, so this is it is given the feed, alright, the FA naught, okay, and also the FB naught enters the well mixed adiabatic reactor at 303 K and the total volumetric flow rate of 10. Alright, so it's given to you also the V naught. Okay, so propylene oxide is a volatile substance and you cannot exceed an operating temperature of 80 degrees Celsius. Okay, so this will be the maximum temperature. Okay, assume that you operate the system at this maximum temperature. Okay, so these are the additional informations given. Okay, this is given the delta H reactions at TR. This is TR, okay, T reference, and also the K at 298K, and also the E as well, the heat capacity for each of the components. The reaction is dependent in propylene oxide concentration and independent of water concentration. It can be treated as a first order and also second order reactions. Analyze and justify the effect of reaction order on the conversion of reaction and volume of the reactor. Okay, so actually this equation, the rate of reaction has been simplified. Okay, whereby it does not depend on the water concentration. Okay, so you can omit this one. Okay, so you need to get the volume and also the X. Okay, assume that first order and second is the second order. Alright, so the difference actually is in terms of the volume, because volume is related with the R, negative RE. Okay, so negative RE for first order and second order is different. Okay, the equations are different. Okay, so look back the what do you call it, the general equation for VCSTR, which is FA naught X over negative RE. Okay, so usually this negative RE will relate with the K value. Okay, so this K actually you need to relate with the temperature, which is using the Arrhenius equation. Alright, so from here you have to find the K. Okay, find the K first, and then you have to find the what is the XEB. Okay, XEB is probably energy balance. Okay, in order for you to substitute all this value into the VCSTR. Okay, so you're going to have two set of solutions, which is for the first order and also the second order. Okay, so this is kind of straightforward questions. And number 2, first order is a liquid phase endothermic. Reaction A forming B plus C is conducted in a CSTR. Okay, so given here is the volume. Okay, operating at a steady state. The feed concentration of A is 1.2 mole per liter and enters the reactor at 8.7 liter per second at 300k. Okay, so this would be the T naught. Okay, and this is the V naught. Okay, and this is the FA naught. Okay, so however, the reactor is heated in order to increase the rate and to achieve of 80%. So the X maximum to be achieved is 0.8. Okay, so you need to determine the temperature needed to achieve these conversions. Okay, so what you have to do is, again, you need to get back how does the temperature related. Okay, so you have to start with the design of equation. Okay, which is V is equal VCSTR. Okay, so this VCSTR is related with the negative RA. Okay, and negative RA is related with the K. Okay, so you need to relate this K, okay, with the Arrhenius equations, okay, in order to get the temperature. Okay, so this would become the temperature outlet lah, maximum. Okay, this is temperature inlet, TI. Okay, so for B is to determine the heat transfer kJ over second, requirement of the reactor to achieve this conversion. Okay, so here means that there is a heat transfer. You need to get what is Q. Okay, so you need to treat this one as non-adiabatic. Okay, because there is a heat transfer. Okay, if it's adiabatic, it does not have heat transfer. Okay, so you can assume this one is 0. You can use the general equation. All right, and you just need to get what is Q. Okay, so the Q you have to get it. Okay, and all of this information you can get it from the informations. Okay, so I'm not sure whether actually this question is given the delta H or not. Okay, so I have to tengok balik. Alright, if there is a missing information, if not, you have to get it from a journal ataupun from the any relevant website to get the delta HRX and CP. Okay, so you have two options whether you can use this one or you can get delta HRX at the specific temperature. Okay, so this one you have to expand the equations. Okay, you have to know what is the TI naught. Okay, don't get wrong with the TRF. Okay, T minus TR. Okay, actually this is an open question, so I just provide to you lah. You just use TR, okay, as 0. Okay, just put it as TR here 0. Alright, and then okay, so it is suggested to add a heat exchanger and a second reactor in a series with the first CSCR. Okay, so the coolant fluid enters and exits the reactor at a constant temperature which is less by 100K from the exit temperature of the first reactor. Both reactors operate at a similar temperature. Calculate the conversion existing in the second reactor given that UA is 2.3 kilojoule per second. Okay, so in this case, you have to consider the coolant fluid. Okay, remember Q is equals to U A T A minus T. Okay, so in this case, TA is not given. Okay, so you have to assume what is TA. Okay, okay, sebabnya TA sepatutnya kena less from the exit T of the first reactor. Okay, sepatutnya TA itulah. Okay, and then you kena to assume what is T. Okay, you have to assume what is TA and what is T. Alright. You can use also, for example, like TA, dia kena, contohnya is 100, which is 288K minus with the 100K. Okay, contohnya lah. Okay, sebab dia nak kena less daripada 100k ni. So the value here you can put it as a T outlet from the first vector ni lah yang you dapat tadi. Okay, from the A. Okay, so I dah terbagi dah jawapan dia. Okay, untuk yang A tu jawapannya around 288k lah. Alright, so from here you have to calculate lah what is Q, tapi disebabkan dia kata dia guna dua Q lane yang sama, okay, heat exchanger. Alright, so you can make it as 2Q. Okay, so here 2Q and still use this all what do you call it, this energy balance equation, okay, in order for you to get the value lah. Okay, so try that to get what is the value of the conversion exiting the second vector. Okay, gunakan balik ni untuk in order for you to get what is X. Okay, so from here ni to achieve the conversion, yang ni dia dah bagi dah X, yang B adalah X equal to 0.8. Yang ni you can dapat what is X. Okay, you kena tahulah guna information ni macam nak dapat FA node, okay, and so on. Okay, CPA. And the other one you also can use other equation. Okay, for example, tak semesti you guna tu. Kalau you dapat in terms of F pun boleh. Mana ya? Jap. Maybe dekat part 3 pun. Okay, yang Q is minus with F and so on tu. Apa, tapi I suggest you, sorry, guna yang ni lah apa yang ada. Okay, sebab theta I nanti you kena expand lah. Contohnya kalau B adalah FB node over dengan FA node. Okay, FC node kita tak perlu fikirlah sebab dia adalah product. Okay, so try to do this one. Okay, I already got you. So you kena try calculate. Okay, if you don't calculate it, I will get very disappointed lah dengan benda macam ni. Okay, so and then we have another one. Okay, this is from the final assessment previous semester. Okay, so an exothermic elementary reversible atomization. Okay, now it involves a reversible. Okay, so kita cari XE lah, mostly dia akan cari label XE. In liquid phase is carried out adiabatically. So dia dah beritahu this is adiabatically in a CXCR. Pure A is fed to the reactor at concentration of 5 mol per liter and feed rate of 100 mol per minute. Okay, so dia dah given what is this CA naught and also what is the feed rate. Okay, which is the FA naught. Okay, as a researcher, you need to analyze the effect of different inlet temperature to the rate of the reaction. The inlet temperature is varied from 50 degrees Celsius, 100 degrees Celsius, and another two inlet in between 70 and 90. Okay, so there are 4 kind of temperature inlet. Okay, perform your calculation based on energy balance and thermodynamic equilibrium conversion in a range of 10 to 130 degrees Celsius, noting that 95% equilibrium conversion must achieve. Okay, so it is given for the KF for forward and K reverse, and also K equilibrium, which is equals to 300, and delta HRXN at the T reference, and also CPA is equal to CPB. Okay, so basically remember, so this one is case number 1, okay, which is T is given. Okay, so you kena start lah with the algorithm. You need to start with the red law. Okay, what is the negative RA net? And then number 2, you kena make it as equilibrium lah, which is negative RA akan equal to 0. Alright, sebab you nak solve XE sebenarnya. Okay, so from here you akan solve what is XE lah in term of XE. Okay, rearrangekan dia lah XE, you akan relate XE dengan KE. Okay, and then number 3, okay, you have to solve lah what is XE. Okay, solve XE. Okay, by using this equation, this value. Okay. So daripada situ you boleh adalah what do you call it, T. Okay, you boleh start lah dengan T berapa. Okay, the starting for 50 kan. Okay, so you boleh lah buat range 10 to 60 ke, 10 to 50 ke. Okay, so you start with first one is TK adalah around maybe you can start it with yang awal boleh start dari 20 degree Celsius, okay, and increase to 50 degree Celsius atau alright, tapi nak start 10 pun boleh, okay, in the range ni lah. Okay, so and then you need to know what is the key, okay. So and then sorry, you can get the what is XE lah, okay, sebab XE akan bergantung pada KE, okay. So KE ni you kena cari untuk setiap temperature yang berubah, and then you can get what is XE. Okay, remember KE ni ada dalam macam dia adalah Arrhenius equation. It's just that dia adalah daripada delta HRF. Sorry, delta HRXN. Okay, instead of EA, dia guna delta HRXN. Okay, so you akan dapat ni. Alright, so daripada situ, what you need to do is you need to get what is XEB from the energy balance. Okay, so Q ni akan jadi kosong lah, adiabatic. Okay, and WS akan equals to 0. Okay, so try to get another one which is XEB lah here. Alright, so from there you can plot what is XE. Okay, ni for example je lah. Okay, what is XE, and you boleh plot XEB here. Okay, XE dengan XEB here. Okay, dapatkan equilibrium adiabatic dia. Okay, so once you get the equilibrium adiabatics, okay, since dia kata note that 95% equilibrium conversion was achieved, means that the one that you get here, XCA, okay, you kena darab dengan 0.95. Okay, so daripada situ, because of apa, you kena dapatkan this one is you need to get a new exit temperature. Okay, sebab ini adalah inlet temperature. Now you want to get the exit temperature sebab kita nak tahu berapa conversion dah achieve dah, which is dekat masa dia keluar lah. Okay, which is 95%. Alright, so daripada situ exit temperature you akan dapat melalui daripada energy balance lah, which is T is equal to T naught plus with the delta HRX times X equal over with the CPA. Okay, so T naught ni you boleh test lah dengan 50 yang kita nak tu lah, which is around 50 degree Celsius. Alright, so we get what is T. Okay, so this T actually you will use in here KF and KR. Okay, in order for you to calculate. Alright, so nombor 8 lah untuk calculate KF and KR. Okay, so that's why make sure benda ni you kena dapat starting SE dia kena betul. Kalau semua salah, T you akan salah. Okay, so once you get the KF and KR, you boleh calculate what is RE. Okay, so buat ni balik, sebenarnya repeat balik untuk 100 degree Celsius, untuk 70 degree Celsius and 80 degree Celsius. So you kena ada 4 temperature ni. Okay, ubah balik kat sini, and then T naught ni berubah ikut pada ni. Kalau 100, 100, 70, 70, 80, 80, okay. And ni mesti within the range. Ikutlah kalau 70 you boleh start dengan 50, 60, 70, 80, 10, okay. So kena test one by one, okay. So daripada situ ikutlah repeat back ni, and then you need to get a set of RA lah here. Okay, so dia ada RA untuk setiap 50, 100, 70, 80. So you kena conclude finding tu. Okay, temperature mana yang okay untuk reaction rate yang untuk increasekan dia and so on. So you kena analyse daripada situ, daripada kuantitatif punya pengiraan. Okay, alright. So for fourth one, okay, this is a previous semester. Okay, about isopropyl acetate, IPAC, is a fine chemical that can be used in a high-end ink oil, okay, and so on. A reversible, okay, so this is a reversible exothermic and non-elemental reaction for the production of isopropyl acetate, IPAC, and water via acetic acid HX and isopropyl alcohol. So IPA acidification was conducted in a fixed bed reactor with entering temperature of 350 K. Okay. So the reaction mechanism is governed by pseudo homogeneous model. Okay, and the reaction heat value is given, which is 5 kJ per mole. So this should be the delta HRX. Okay, at this temperature. With the equilibrium constant, okay, which is Ke is equal to 23 and the temperature is 333 K. Okay, so the change in heat capacity between IPA and HX as the and internal pore are assumed to be negligible. Okay, so tak perlu tengoklah heat capacity untuk benda ni. So since the increase of diabatic conversion is possible on the adiabatic reaction equilibrium by using internal heat exchange method, evaluate the temperature conversion shifting via interstage cooling. Okay, so you kena buat graph of XE versus T, but you need to indicate the interstage cooling within that curve lah. Alright, and you need to propose berapa banyak what they call it, reactor ataupun coolant yang diperlukan lah. Write down all the assumption made and draw clearly your proposed interstage cooling. Okay, so this is a PFR. Okay, and IPA is assumed to be the key reactant or limiting reactant despite molar ratio between IPA and HX of 1:1. Okay, consider water and acid are inert in the product, zero order of reaction. Heat capacity for IPA is 5 J per mole per K. So means this one, for the other reactant, this one considered as zero order. So what you have is only this. Okay, so IPA, alright, is a reversible with to form IPAC. Okay, which is you can name it as B. Okay, so again, what you need to do, tengok balik kat part 3. What is the step to get the interstage cooling? Same sahaja, sebab at the end dia nak dapatkan what is XEX, alright, versus with the temperature. Okay, so step 1, you memang kena ikut algorithm lah. You kena buat, know what is the red law. Okay, derive the red law punya what do you call it, equation. And then step 2 is make it as equilibrium. Okay, and then step number 3 adalah kena buat stoichiometry lah. Okay, and you need to express lah XE in terms of KE. Okay, sebab KE ni kita nak derivekan dia sebab dia akan relate with the temperature. Okay, so number 4 is you need to get what is a KET. Okay, so KE will what do you call it, will change according to the temperature. Okay, so you need to have a temperature range. Okay, so from here it is 350 K. So you boleh buatlah starting from equals, but this is open question. Okay, maybe you can start 298 until 750 ke, and so on. Okay, so that you can have a range here. Okay, sebab ingatkan kalau kita nak buat intercooling, kita nak buat yang zigzag ni, kita kena ada what is the starting here. Okay, alright, and it must have a maximum here in order for dia nak reach lah. Turunkan dia, naikkan balik, turunkan dia dengan temperature. Okay, so from here you'll be able to get what is XE lah. Okay, sebab XE ni akan berkaitkan KE daripada sini. Okay, daripada mass balance law, daripada red law tu lah. Okay, so daripada situ you boleh dah tabulate lah what is, this is TK, alright. Okay, start at 298 sampai, letaklah range berapa yang you nak. Okay, and then tapi must be more than 350 lah. Maybe you can double it atau triple kan dia ke, dia 900 ke 800 ke, ikut you lah. And then we have a KE, and then we have a KE tak nak ganti function T and also XE. Okay, so daripada situ of course you kena cari what is XEB lah, sebab kita nak dapatkan graf ni kan kita kena ada line untuk XE dengan line untuk XEB. Alright, so XE ni dapat daripada red law of the what do you call it, of the reversible, and XEB is from the energy balance. Okay, so you can put it as this one is XEB. Okay, so daripada situ you kena plot lah. Okay, plot. Alright, and CP given here actually kalau saya tengokkan dekat as a scheme, heat capacity ni adalah bukan dekat temperature 350. Okay, this one is dekat different temperature. Okay, so you kena cari CPA untuk CP untuk reactant. Remember kita ada, I tak ingat nama dia, which is ada A plus B T squared plus D. Okay, so you kena masukkan the temperature here. Okay, which is 350. Okay, masukkan untuk dapatkan CPA. Okay, so daripada situ sebenarnya you boleh calculate SEB. Okay, sorry I terlepas dulu, ni sebenarnya nombor 6 dulu. Ni nombor 6, ni nombor 7 lah, sebab nanti CPA ni you akan masukkan dalam SEB. Okay, daripada energy balance. Alright, so daripada situ ni nombor 7, ni nombor 6. Okay, so nombor 8 you boleh plot lah. Plot XE and XEB versus time. Versus temperature, sorry, temperature. Okay, and then nombor 9 buatlah interstage cooling. Okay, sampai dia nak reach maximum temperature yang dia boleh lah. Alright, okay, so I think that's all. Alright, I hope this guideline will help you to do the tutorial. Okay, so make sure I don't like you to last minute study. Okay, dan nak exam baru nak study. Okay, you better to do it. Okay, before the revision week. Okay, and so that we can discuss during the class. Okay, kalau benda yang awak tak faham, you can try to ask me lah during the class, much better. Okay, so that everyone can also learn. Alright, okay, so that's all from me. Okay, stop sharing. Okay, all the best. Okay, bye. Assalamualaikum.